Hello students, today we are going to discuss about the scattering theory in quantum mechanics. So in the first section we will study about the scattering, what is scattering and what is mean by cross section. In the later stage we will study about the different scattering angles connecting the lab reference frame and center of mass reference frame. So starting from the scattering, so why scattering is important? Much of our understanding about the structure of matter is extracted from the scattering of particles. It was not be possible for us to study the structure of microphysical world. Similarly, through scattering experiments, that is we know about through scattering experiments that is important building blocks of matter, such as the atomic nucleus, the nucleons, and various quarks which we today they are in our knowledge. So they all these because of scattering theory. So in the first we will know what is scattering. What is mean by scattering? When a beam of particles are allowed to bombard on some target particle or target material, then the incident particles or the projectile particles scatters are deflected from its straight path. This phenomena is called scattering. Experimentally, if we want to study the scattering effect, let this is a material particle, a target particle which has some mass, let's suppose m2, and it is an incident projectile particle whose mass is m1. Let this m1 or the projectile particles is allowed to fall on the target particles, then it deflects from its straight path, and here a detector is placed. In the experiment, here is a detector D which detects the scatter particles at various angles. So the angle by which the incident particle is deflected from its straight path is called scattering angle. So the scattering phenomena can be discussed classically as well as quantum mechanically. In classical physics, when we are studying the scattering, then we assume the incident particles and the target particles to be particles. We assume these to be particles. On the other hand, quantum mechanically, the target may be considered as a region of some potential VR. For example, let's suppose we have a target particle of, let's suppose, helium, which is double positively charged nuclei, and let's suppose here is a proton, and it is allowed to fall on the target. So classically we consider them particles, but quantum mechanically this will be a region of some potential. So the target is assumed to be a region of some potential, and the region where the incident particle experiences some Coulombic force, is this region is known as potential region. And the incident particles, quantum mechanically we consider them to be waves. So the incident beam is considered to be plane waves, and the scattered beam, which is also a particles, and quantum mechanically these are actually spherical waves. These are spherical waves. The scattered wave will consist of both the unscattered beam, because some particles may pass through this region without deflected, because there will be no interaction of some particles and they will pass straight through the region, and some particle will be scattered. So the scattered wave will be the sum of the spherical wave plus plane waves. So next we are going to study about the cross section. What is mean by cross section? So here in experiment, the detector detects some scattered particles or scatter waves, if we are talking about quantum mechanically. So the detector placed here will detect some scattered wave. So that scattered wave is passing through some region. For example, if we draw it like this is the incident particles, the incident beam, and here is a target, and let's suppose here is the detector. So the scattered wave in this region of solid angle d omega at an angle theta and phi. So we are going to calculate, let's suppose at this point the detector is placed here, so we are going to detect or measure the particles scattered in a solid angle d omega along the direction theta and phi, in this direction. So the number of particles scattered into an element of solid angle d omega. The number of particles into an element of solid angle d omega in the direction of theta and phi, this will be proportional to the number of incident particles. This is if we represent the number of particles in this direction. So if we represent them by dn, this will be proportional to the incident flux, where this j incident, it is called incident flux, and it is defined as the number of incident particles, per unit area per unit time. Here we stated that the number of particles scattered into an element of solid angle d omega is proportional to the incident flux, and incident flux is the number of particles per unit area, the number of incident particles per unit area per unit time. Also this dn is proportional to d omega, the element of the solid angle. The larger the size of the detector, the larger the detector will detect the particles. Similarly, for a smaller region of the detector, it will detect less scattered particles. So if we combine these two equations, we can write it as dn is proportional to j incident d omega. By replacing the proportionality by some constant, and that constant is assumed to be d sigma over d omega. Here we talk about the number of particles scattered in the direction of theta and phi. So we will write here theta and phi, because this particle, it depends on theta as well as phi. Theta and phi, theta and phi. And j incident d omega. Here this constant of proportionality is called differential cross section. So we can define the differential cross section as, here this is called, this proportionality constant is called differential cross section. So we can define the differential cross section as d sigma upon d omega, which is equal to d n. From this equation, this will be equal to dn, which is a function of theta and phi, upon j incident, the incident flux, and d omega. This is equation number first. Thus we can define the differential cross section as, this is called the differential cross section. We can define it as, and it is denoted by d sigma upon d omega. It is defined as the number of particles which are scattered into an element of solid angle d omega in the direction of theta and phi per unit time per incident flux. If it is cross section, then we have to check its dimension. So to check its dimension, this is actually number of particles. So the number of particles, its dimension is number of particles per unit area. And incident flux, by definition we define incident flux as the number of particles per unit area per unit time. So this will be n number of particles per unit time per unit area. And d omega is actually solid angle, and solid angle is dimensionless. It has a unit which is steradian, but it has no dimension. So n upon a will cancel with n upon a, and we will left with 1 over 1 upon a. which is A. So the dimension of the differential cross section is area, so we can say it is an area. The total cross section which is represented by sigma, it is obtained by integrating the differential cross section with respect to omega. So d sigma upon d omega into d omega. And the definition of d omega is actually a solid angle. It is called solid angle, and its value is sine theta d theta d phi. So we can write it as the total cross section sigma is double integral, because d omega is a function of theta as well as it is a function of phi. So it will be, this will be d sigma upon d omega, and this d omega can be written as sine of theta d theta d phi, and the limits are from 0 to phi, which are for theta, and for phi these are from 0 to 2 phi. We can also write it as integral from 0 to phi, which is for theta, which is sine theta d theta into integral 0 to 2 phi d sigma upon d omega d phi. So if we are going to calculate the total cross section, first we have to integrate the differential cross section with respect to phi, and then we have to integrate it with respect to theta.